This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Correct? Yes? When it's measuring S11, what's it doing? Did they draw you a diagram of what a vector network analyzer is actually doing? I'm sure they did, or they explained to you what was happening, right? So essentially what the vector network analyzer was doing was putting a signal of certain current and voltage into the one port, and on the other port what it was doing was it was switching the 50 ohm load. So therefore one of the loads, so on port 2 if you're measuring S11, essentially all it was doing was exciting port 1, was measuring the reflected voltage, but specifically what it was doing was terminating port 2 with a 50 ohm load. So it was switching in a 50 ohm load and putting it there as part of that process. Okay. Did you guys get a schematic of how the VNA looks? You know, as a basic concept? What I'll do is I'll find you some, I'll draw something and I'll put it on the lecture notes. Oh, and that also reminds me, just because I've forgotten, I've also put the solutions to the example problems online, right? So you've all seen that? Good, all right. And likewise, we measure S21, which is essentially the voltage that we get V2 coming out of the port when we excite with V1 going into the port. That was the definition of S21. S12 was the opposite, which was essentially we excite port 2, or sorry, what we excite in port 2, what's the voltage in 1, and likewise S22 was the reflected coefficient. Now we said specifically for some lossless networks, what we've got is the following relationships hold, which is S11 squared plus S21 squared equals to 1, and S22 squared plus S12 squared equals to 1. And then I asked you, I can't remember if we went through this, but I asked you to work out the scattering parameters for a simple resistor, or sorry, a simple impedance. Who went through the process of actually determining that? Did I go through it, or did I give it as a homework exercise? I think I said do it as a homework exercise, didn't I? Can someone remind me? We went through it? No. Okay, so I signed that as a homework exercise, is that right? Okay. Now, good. So I asked you to work out the S parameters for the simple, most simple of networks, right? And what do we know about this network? Well, it has to be reciprocal. So we know that S11 equals to S22 and S12 equals to S21. How do we know that? It's a resistor, right? It's a simple impedance. If you put, it doesn't matter which direction you excite in your measure. It's symmetrical. It's almost symmetrical. You know, it's symmetrical. That's all I'm saying. It doesn't matter if you define this as port 1 and you measure at port 2, or if you you excite at port 2 and measure at port 1. It's the same thing, right? It's a passive lossless network. Okay. Then I asked you to work out S11, which by definition was V1 minus on V1 plus when V2 plus equals to 0. And specifically, I stated that this situation occurs when the output port is matched, right? So therefore, what we do here is actually, in order to calculate S11, we add Z0, or we switch in a Z0 to the output port, right? That's where that extra Z0 is coming from, right? I'm getting a lot of confused faces. You're worrying, all of you are worrying me. Does that mean that you understand this, or I'm not explaining it properly, or Just continue? All right, good. So therefore the total impedance in this particular case, if we're looking into measuring the reflection coefficient, is we're going from Z0 to the total impedance here is Z plus Z0, because we had to, remember when we're calculating S11, we said the definition, it's a definition, it's nothing magic, right? It's the way that we've defined S11 is that we terminate it with the characteristic impedance. And that's why you went through the process of having a workshop on vector network analyzers, because what that specifically does is it actually terminates, you know, that circuit that you're measuring with, you know, a load equal to the characteristic impedance. Okay, so when you do this, you can actually show that gamma is Z in minus Z0. You remember that? You go through the process. So therefore, V1 minus on V1 minus on V1 plus, when V2 plus equals 0, is Z on Z plus 2 Z0. Nothing special, right? Very simple to calculate. Likewise, we want to calculate S21, and we go through the process of being able to calculate that, and we've said the definition of the S21 is V2 minus on V1 plus when V2 plus equals to 0. Again, what that means is we've actually here terminated port 2 with an impedance equal to the characteristic impedance, and we know generally V2 is equal to V2 minus plus V2 plus. It's nothing special, it's just the way that we calculate it, but because it's terminated because it's actually matched, we know that V2 plus equals to 0. So therefore that says essentially that V2 minus, which is what's actually going into the, which is actually leaving the port, is equal to Z0 times the current. Likewise, we've got a relationship for V1, which is V1 plus V1 minus. We know that V1 minus is related to V1 plus by the reflection coefficient, which in this particular case we've determined it to be equal to S11. So essentially we've got V1 is equal to V1 plus, you know, times 1 plus S11. Right? Again, nothing special. And then likewise, when we continue through the process, we get to the stage where we've got S21 is equal to Z0, I0 on 1 plus S11 on Zn times, again, times I0 or I. So once we cancel out, what we find is S21 for this very simple circuit is 2 times the characteristic impedance on the impedance of that particular, the impedance of that element that we had in the circuit times plus 2 times the characteristic impedance that we've terminated in. Okay? So essentially what you're able to do now is go through the process, and given some very simple circuits, you can actually work out the scattering parameters. And the point here was essentially that you're able to try to relate some of the standard concepts that you've got, for example, impedance and admittance, to scattering parameters. Right. Now, the truth of the matter is, we've gone through all this work to show you what the relationships are, but generally what happens is if you're given a network, what you find, like in Poser or some other text, is you'll find formulae which translate from either admittances to scattering parameters or from impedances to scattering parameters. Okay? All right. Now, what I'd like you to do is, as I said, you can actually look it up in Poser, but what I'd like you to do, just as a homework exercise, just sit a few minutes, or whilst you're drinking coffee or tea or whatever you guys like to drink, work out what the scattering parameters would be for this admittance. Right, just go through the process. The answer is in Poser anyway, or you can look it up on the internet. It's very simple, but I would strongly recommend you go through the process, so therefore you can now build an intuition on how, again, a impedance and or admittance relates to scattering parameters. Okay. Now, let's look at a general circuit, and we're going to use this. The reason why we're doing this is we're going to use this as our foundation for a lot of the work that we're doing in amplifier design, right? So, in many cases, what you've got is you've got a generator, you've got some kind of matrix here, or some kind of element, and here, in this particular case, what we're saying is this element has a set of scattering parameters, and it's connected to some load. And essentially what you want to do is to calculate, if you're looking into this port, what its input impedance is, and you want to know if I'm looking into this port, what its output impedance is. Why do we care about input and output impedances, generally? Yes?
Because if you want to use it as instead of big circuits, then we need like figure out, I don't know whether we need a voltage buffer or something, connected to a small impedance later, or we need to match impedance.
Sure. Yeah. So generally, when you're trying to feed, how do you call it, a network, you want its input impedance to be, conjugately matched, so that you can get maximum power into this network. And also, in most cases, you also want the output impedance to be matched to the load, right? And if you're talking in DC, if you were talking about DC, what would you want the source impedance to be? Right? Forget about, in AC, here we're talking about high frequency, we're talking about conjugate matching. Suppose you were in DC, very low frequencies, what do you want the output impedance to be? Generally.
The load impedance.
Sorry?
The load impedance.
I mean, that's if you're conjugately matching, but generally you want low output impedance, right? So you want high input impedance, so therefore you don't suck any current, and low output impedance, so therefore you can suck as much current as you want without increasing the voltage, right? That's what you do when you're doing DC circuit design, in very low frequencies, right? Anyway, so here what we're doing is, because we want to maximize the transfer of power between the source in our network and then also from our network to the load, what we're going to do is we want them to be appropriately matched. So now let's calculate this input impedance. The reflection coefficient looking into this load and the reflection coefficient looking into the output port of this, input impedance looking into this network, or the reflection coefficient looking into this network, and the reflection coefficient looking into the output port of this network. And essentially, in order to be able to calculate that and to actually work out the relationship, usually what you find is books, they just write this formula down, right? And usually you look at it and you go, where in God's name did they find this? Where does it come from? What does it mean, right? So that's usually, I just remember back to my third or fourth year, and just, the lecturer wrote it on the board, and it was something I just had to learn. But, at the time I was like, where does it come from? What do I do with it? What does it all mean? So I'm giving you a little bit more insight onto how to be able to derive it, but also to give you an understanding where it comes from. So let's now consider this network, right? And let's now look at this two-port network. And what we're going to do is we're going to have, essentially, we want to work out the input impedance. And what we're going to do is we're going to excite the port with V1 plus. So we got V1 plus. And what we're going to do is we're going to have, something connected, a load connected into to this network. So we know that because it's a linear system, we're going to have V1 to V2 minus is going to be related by S21. We know that V2 plus is related to V1 minus by S12. We know that V1 plus leads to V1 minus through S11. V2 plus goes to V2 minus through S22. And then we've got the load reflection coefficient here. So this actually signifies all the signal paths that we have in this particular network, right? So let's now go through the process of deriving this. So therefore what we say is gamma n times V1 plus is equal to V1 minus, right? So how do we also calculate V1 minus? Well, V1 minus is, if we look at this graph, V1 plus times S11, right? And we also know that V1 minus is equal to V2 plus times S12. Great. But now what we want to do is we want to rewrite this. We want to be able to get rid of this V2 plus. So let's look at this V2 plus and see if we can write V2 plus here in terms of V1. Now we know that V2 minus, right, is S21 V1 plus S22 V2 plus, right? And we also know that V2 plus is gamma L V2 minus, right? So we can write that there. And if we take the V2 minus all to the one side, we get V2 minus is equal to S21, 1 minus S22, gamma L V1 plus, right? Now, what we're able to do is we know that V2 plus is gamma V1 V2 minus, so we can actually, or gamma L V2 minus, so we can actually replace that in order to have this in terms of V2 minus, and then we know what V2 minus is, so we can put all that into here. So we've got now gamma n V1 plus is this relationship of V1 plus. We divide through V1 pluses, so therefore we've got the input reflection coefficient is equal to this relationship. Oh, sorry. You should tell me sooner, because otherwise I've been drawing there thinking that I've been explaining it and I haven't. Okay, does that make sense? So all I'm doing here is drawing the signal graph, right? And all I'm doing is working out the relationship between the voltages at each of these nodes in terms of the other voltages, and then simplifying out in order to be able to calculate the input reflection coefficient. I also do the same for gamma out, right? And here I've written it in terms of gamma source, and once you do go through the whole calculation, what you're able to show is gamma out is equal to S22 plus gamma S, S12, S21 on 1 minus S1 gamma S. Now, this is actually showing you the relationships between the input reflection coefficient and the output reflection coefficient in terms of the reflection coefficients at the source and at the load, and also the scattering parameters of the matrix or the network that you have between the source and the load. Okay. Now, what I'll do is I'll continue with this process in order to be able to calculate a few other very important concepts that we require as part of our power amplifier in order to be able to analyse and design power amplifiers. Now, the next thing that I want to be able to talk about is what's the power into a network in terms of these input and output going waves. So if I had an A and a B, right? So if I had A going in and B going out, what's the power that's, and A is defined to be, and B is defined to be. What's the power going into that network? Can we see? All right. I mean, I've written it there, but I want somebody to explain it to me. I mean, yes, I've written some mathematics on there. I could be completely nuts also and written some random stuff on the board. Can someone tell me, what am I doing there? Sure, right? So I've got a signal going in, right, which is V1 plus, which is the power that's incident onto that port. We know that some of the power is going to be reflected. So I've got the incident minus the reflected power, and we know that there's a relationship between the input power to the output power, so we can actually rewrite it in terms of the, V1 plus and the input reflection coefficient. Great. Okay, so therefore, that tells us the power that's going into a network. Now, I'm going to talk about what's the difference between this and the next concept I'm going to talk about, which is the power available from a source. Okay, so I've got a network. Okay, so here I've got a signal. Let's assume we've got a signal generator, and I'm connecting some network to it, right? With some magical load, right? And here, in the first particular example, what I'm doing is actually working out what's the actual power that's going into here. How does this differ, the input power, differ to the power available from the source? Somebody? Okay. Essentially, what I'm saying is, what's the maximum power that's available from a source, right? So remember, here we have to use okay, let me ask you the following question. What's the maximum, when do I achieve maximum power if the source impedance is fixed? When the load is, what's the relationship between the load and the source impedance in order to get maximum transfer power? It's close, but not exactly. It's equal if it's real. What happens if it's imaginary? Sorry? It's conjugately matched. Right? That's the only thing I was trying to make sure that you said. Okay. That's when the maximum power occurs, right? And we talked about that's maximum power transfer occurs when the load is conjugately matched to the input impedance, or the source impedance. And then, and specifically we said that only occurs, or that theorem only applies when the source impedance is fixed. And in this particular case, what I'm saying is, hey, we've got a signal generator, it's got a given source impedance. When do we get the maximum power transfer? Well, the maximum power transfer is when it's the load impedance is conjugately matched. So that's essentially what I'm asking you to calculate in terms of scattering parameters, right? So essentially what I'm saying is, what's the maximum power that's delivered by a source that's conjugately matched to the input impedance of that network? And essentially what I do is go through the process of being able to calculating this in terms of the input and output voltage waves and the reflection coefficient at this particular location. So once you go through that and show what you're able to show is that the power that is available from the source is equal to essentially the power that the source generator is generating, and 1 minus the reflection coefficient between the source and the input to the network. Right, so this is the total available power. Right. Just to make sure, can someone tell me what's the difference between input to the network and available power? Just in words, because it seems like I remember back in my day I was very confused. So I just want to make sure that you guys are not confused. Yes.
Between like all the power that arrived at the beginning of the load and the power that comes out of the source.
Sure. So one of it is, hey, I've got a specific network. That's the amount of power that's going to go into that network. it's for a specific network. The other one's saying, hey, for any network, what's the maximum power that I can get from this source? One's actually giving you the information about the source. The other one's saying, for this combination of generator and network, this is the maximum power that's actually going into that network, right? It's important because once we define some of these transducer gain and power gain relationships. You know, they depend on available network, power to the load, and the like. So therefore, I just want to make sure that you guys have a good grasp of what each of those major concepts means. Now, likewise, you can go through and convince yourselves that that you can rewrite the power to the load in terms of, and this is to the load, not from the source to the network, what the power delivered to the load is in terms of the load reflection coefficient and the voltage at the output port, V2, and also the power that is delivered to the load when the load is conjugately matched, right? So there are our definitions. Now, what I'm going to define is going to be the following, and we're going to define transducer gain, right? Which is the power that's delivered to the load versus the power that's available from the source, right? That's the definition of transducer gain, and this is the relationship that you have. Now, you can actually derive this quite simply given the data that I've given you, or the formula that I've given you. And you can also rewrite this formula not only in terms of the load, you can rewrite this formula in terms of the reflection, the source reflection the source reflection coefficient and the load reflection coefficient and the output reflection coefficient. Now, likewise, you can define, what we'll do is we'll define power gain, which is essentially the power that's delivered to the load to the power that's input to the network, and you can actually show that this relationship actually holds. And we can also talk about the total available power gain. Okay. Does anyone want to, in words, describe to me and to your colleagues what the significance of each of these is? You're all very quiet today. I'm just trying to, is it? Okay, not to worry, just, okay. Okay, so here what we're saying is, what's the best I can do, right, for the particular generator that I have available, what's the best I can do in order to transfer power to the load, to the specific load that I have. Here, what I'm saying is, given I've got a fixed input impedance or input power to my system, what's the maximum power I can deliver to the load, right? This is, if I had the best choice, if I could arbitrarily choose the input impedance to my network, essentially that is the best. Transducer gain actually tells me the best that I can do from getting the power from the source and delivering it to the load. Power gain is essentially the definition where, for a given input impedance, what's the best I can do in order to deliver the power to the load. And essentially, if I was able to choose my input and output impedances as I so desired, this allows me to work out what the total power gain that I can get out of that particular network or transistor. All right, and these are all going to be very important concepts when we're defining transistor amplifiers. All right, and on that note, let's start talking about some exciting transistor amplifiers. Who of you has built an amplifier? Good. Yes? Yes? Okay, so what did you design? What kind of amplifier did you design? Sorry? Op amp. Okay, so you just put a couple of resistors in order to... Okay, all right. Okay, so that works very well. What dictates how fast or what frequency you can make that amplifier work? Why wouldn't you use it at very high frequencies? So if you've got an op amp, someone gave you an op amp, right? A real op amp, not this symbol, right? Because this symbol doesn't really exist in real, all right? So I'm saying, so you've probably had. Right, so this is probably, and that's an inverting amplifier, right? What dictates the frequency at which you can operate this at? Why couldn't I input, if this is a real op amp, like a 741 or whatever it is, why couldn't you, if I draw this symbol for an ideal op amp, this relationship, the gain, which is R2 on R1, hopefully minus R2 on R1, applies for all frequencies, right? If it's an ideal op amp. Correct? Yeah. What dictates what frequency I can actually operate this at? This won't have infinite input impedance for all frequencies, right? And it's also got a finite transfer function and like. Anyway, what you should do is, you've been taught this in what, one of your other classes, I bet, right? And you've designed a power amplifier. What I would do, what I suggest that you do is look up gain bandwidth product, right? And then actually see at what frequencies can I actually use this circuit in order to do amplification. Because if you go, like for example, if you look at a 741, if you go past, say, a megahertz, doesn't provide any gain, right? Now some of the others might go up to 10 megahertz or 100 megahertz, but what I'm asking is look up and see what dictates what the maximum frequency at which that operates as an amplifier. How do you define it, or how do you determine it if someone gave you a data sheet? Okay. Now, what we're going to do here is we're going to do, well, and if you look at this, this is a very complex circuit. If you look at it inside, right? If you look inside the 741, there's the output drive stages, high impedance input stages, stages in between in order to, to do a whole bunch of things, and there's temperature compensation, there's a whole bunch of things, right? So if we've got, in this particular case, what we're going to do is we're going to look at, well, how do we design an amplifier? And in particular, what we're going to do is we're going to design amplifiers where either we're given an amplifier or a transistor, and for that amplifier or transistor, we're given the S parameters or the scattering parameters for that particular element, right? So that's what we're going to do as part of this part of the course. Now, in order to make this work, has anyone used a high frequency amplifier before? Or even one of these, but not a 741, and operated it at, trying to push a capacitor or drive a very capacitive load? No? Okay. Okay, so there's a couple of things that we want to do. One is we want to design, as part of this course, or this part of the course, we'll be designing power amplifiers. You can either be given an actual power amplifier, or you can actually be given a transistor. And in this particular case, we'll talk about the scattering parameters of either an amplifier or a transistor. And, in order to make things relatively simple, what we'll do is we'll consider a transistor-based amplifier. You can actually even build an amplifier using a simple transistor, right? A single, Now, in order to get that to work, like if you're looking at Poser or if you're looking at any of the other books, one of the things that's important to realise is when they're giving you the transistor itself, what they're not showing you is all the biasing circuits around that transistor. Does everyone know what a biasing circuit is? Perfect. All right. So what they're doing is they're not showing you the biasing circuit, which is, at least for a transistor, you know for a fact, in order to get current gain, in order to get the transconductance, you need to have current going through that transistor in order to have a GM. All right. And all I'm saying here is when you're looking in Poser or a lot of the books that are doing power amplifier design, what we do is because they're all operating at DC and not at high frequency, we throw that away in order to simplify the analysis. Okay. So here, what we'll do is we'll look at simple transistor amplifier circuits. You know, just to emphasize, because I think this is important, especially when you're looking at it, you know, in order to get this transistor to operate as an amplifier, you need to bias it. You know, there's going to be, of course, a lot of questions on how do you design one. You know, but the important things that I want you to learn here is, of course, if you've got a transistor and you bias it, what you're able to do in order to be able to use it in order to design an amplifier using the techniques that I'm about to show you is that I want you to be able to, you need to have these scattering parameters. And essentially what happens is when you look at a transistor and you look at a transistor data sheet, I've given you an example of this on your notes, on your lecture notes. I've just chosen an example data sheet, right? Nothing special other than this is an example data sheet. And for this example data sheet, what you find is, especially if it's a high frequency, if you're trying to operate that transistor at high frequencies, what they do is they actually give you the frequency and the scattering parameters, right? So for example, if you wanted to design an amplifier that operates at, say, 3 gig, what would we do? What do you think we would do? Well, we'd say, well, in this particular case, if we want to design, well, we need to put, in this particular case, it's a BJT because it's got a collector and an emitter. What we need to do is place 1 volt across the collector and emitter and a collector current of 5 milliamps. And if we have those biasing conditions and we want to operate this circuit at 3 gig, well, these are the scattering parameters for this particular device, right? And what we'll do is we'll talk about gain and gain of the circuit and the like. But essentially, this is telling us, hey, if I've got a transistor and I've biased it, these are the scattering parameters. All right? Now, if I've got these scattering parameters and I want to, let's go through an example. Oh, I've mixed up the, I've mixed up my slides. All right, maybe, no, it's fine. Okay, so I'll say to you, well, okay, I've got a transistor and it's got these characteristics, right? I've biased it appropriately. And what I've done is I've got the following input and output matching networks, which have the following characteristics. It's got a reflection coefficient of 0.5, 120 degrees, gamma L of 0.4 and 90 degrees. I'm asking you to work out the power available from the source, the power available from the input into the network, the power available from the network, and the power available to the load, right? So in order to be able to do this, based on what we've determined so far, the very first step that we need to do is determine gamma in and gamma out, right? So essentially, this is just a whole bunch of mathematics or algebra. So once you do that, you can actually work out your input reflection coefficient, which is 0.627 and minus 164.6 degrees. And likewise, gamma out is equal to 0.471 minus 97.63 degrees. All I've done so far is we've derived in the earlier part of the lecture what gamma in and gamma out were in terms of scattering parameters. Now all I'm doing is just doing a substitution given the values that we have available to us. Right. Then I've asked you to work out a few other concepts, but because it's all new and fresh in your minds, what I'll do is I'll just put these three formulae up there as quick refreshers, which was the transducer gain was P load on P available from the source. GP was again PL divided by the power to the load divided by the power input of a network, and available power gain was available from the network power available from the network to the ratio to the power available from the source. Now we'd worked out these calculations for GT, right? I'd given you the formula, I'd gone through the process of actually working that out. And essentially what I'm doing is I'm just resubstituting in here. And what we find is for this particular transistor, right, with these particular characteristics, with this source and load reflection coefficient, once I substitute everything in, I can get 9.75 dB of gain, transducer gain, or the available power gain was, again, you know, if we go through the calculations, and you can just calculate these. Assume you all know how to multiply and add phases, right? You should by now. There shouldn't be any excuses for not to. But anyway, just make sure that you go through that as part of your, you know, your revision. You can work out GP and GA, right? Now, I want to work out. Remember, I want to work out PL, PAVN, PN, and PAVS, which is power available from the source. So we know that the power available from the source is just V squared on 8. Good. 8 times the impedance of the generator, right? So therefore, we can go through that calculation when we, and in this particular example, I've said the voltage is 10 volts, the impedance of a generator is 50 ohms, and what we can actually show is that the total power that's available from the source is 0.25 of a watt. Right. Now, that's excellent because that gives us one bit of information. So we also know that the transducer gain is power on the load divided by the power available from the source. Very simple mathematics. We can now work out what the power that's available to the load, right? So that's just 9.43 times 0.25 watts, which is the power available from the source. So therefore, the total power that's available to the load is 2.358 watts. Likewise, we can use the relationship for GP, which we calculated to be equal to 13.51, and we know that the power to the load, GP, is equal to power of the load divided by the input power. Again, changing in order to make P in the variable so that we can actually determine that variable. It's 2.35 divided by 13.51, which actually tells us that the power into this network is 0.1745 watts, and then also the power available to the network, again using this relationship, is 2.39 watts. Right, so all I've done here is, it's very, very simple. I've just used these definitions in order to work out transducer power gain, available power gain, for the various combinations of for this particular circuit in terms of the scattering parameters and the input and output reflection coefficients. And then what I've done is I've actually said, well, if I'm given a transistor with these particular characteristics, if it's been biased and has these particular characteristics, I can then work out what the input-output powers are going to be. That's all I've done, right? Now, the next thing that I'm going to do, and I'll just introduce it, and then what we'll do is we'll talk about it in much greater detail in the next lecture, tomorrow, is what happens once I've got this two-port network, right, which has got some kind of microwave transistor. And there's a couple of things that I want you to think about tonight. One is, if I've got a two-port network and it's active, can the impedance ever be negative? Right? So I want you to think about that. I won't give you the answer, but if you look at the notes, it becomes obvious why I'm saying it, but nonetheless, I want you to think about it. Can an impedance ever be negative? The real part of an impedance ever be negative? Right? Yes or no? Yes. Yes, perfect. Now think about it. Why? All right, just think of, so the only thing I'll say is I think that there's a little bit of a discussion between those two individuals, which I think they're trying to decide if it can or can't be, and the answer is yes, it can. Resistor is loss. What's the opposite to resistance? Instead of having loss, you can have gain or amplification, right? Right, and the other thing is, of course, that these amplifiers can be unstable, right? Depending on either the input or output impedance, what can happen is a network can become unstable, right? What does it mean to have an unstable network? And I'll finish with that concept. Yes? All right, so you can have an oscillation. When you talk about stability in control systems, right, because I'm sure our department loves control systems, what's usually the definition of instability? Sorry? Yeah, but what does it, okay, so you're right-hand playing poles, yes? And what does that mean in terms of a solution? If you've got a right-hand side pole, large, and it goes larger and larger and larger and larger, it goes to infinity. It can either go to positive infinity or between positive and negative infinity. Let me ask you the following question. Suppose this op-amp became unstable. What's the maximum and minimum voltage that it will ever achieve? I'll let the other people that are the control theorists amongst us tell me. What's the maximum and minimum voltage that it can ever achieve? Right. It can never get, it can go a little bit or a little, so it's really the supply range, right? Now, technically, you might have ringing or it gives it, you might go a little bit above the rail or a little bit below the rail, but generally, you don't go much above or below the rails, right? Your supply voltage rails. So, you know, unlike control theory where you've got a right-hand plane, right-hand pole, a plane, right, a pole in the right-hand plane, which, you know, if you do the mathematics, it goes to positive infinity or, you know, positive negative infinity, depending on it's oscillating. That never happens in practice. In a real amplifier, you're going to hit the supply rail and it's going to stop. You're going to hit the negative supply rail and it's going to stop. It'll click. Right? Anyway, just a little bit of information. Okay, and from that note, let's talk tomorrow, and we'll talk about the concept of stability, unconditional stability, and tests for stability. yeah. So what I've done is it's exactly. Yeah.
But what's actually this calibrated impedance?
So I can make it a power wave. So that's why I'm dividing it by the characteristic impedance, which is the 50 ohms of the.
Yeah, so this calibrated impedance is actually the calibrated resistance of the.
No. It's usually the characteristic. In this particular case, usually you choose it to the impedance of the generator. Yeah, the thing, the line that you're delivering it. But generally, what you do is you have it relative to your vector network analyzer or whatever, and that's what chooses your characteristic impedance. So you've got to choose your characteristic impedance in this particular case, which is the thing that's feeding the network.
Okay, so it means that the calibrated impedance is feeding the generator.
Yes.
So actually, this means that it is divided by the calibrated impedance.
If that's
of the generator.
I mean, yeah, but here, if it's a voltage, what I've done is because I was writing it, and then depends, right? So if you can either have a voltage, right, or you can have which is a power wave, right? So I've normalized that as a power wave.
Yeah.
That's all I'm doing.
So the BS actually means actually indicates the calibrated impedance of the
Yes,
source.
yeah. It also already includes that. What I'll do is I'll add another slide. I realised after I wrote it, that I needed to add something else. So what I'll do is I'll add another slide in there.
That's right. And also, so will these ones actually? I mean, will the losses is matters to this one? I mean,
They're not lossless. These are lossless lines, right? Z noise.
so when we use this, we assume there's a lossless line.
Yeah, that's what I'm assuming. I'm assuming this is a lossless characteristic line with characteristic impedance.
Okay.
Right. So really, what I'm saying is there's a line that's got L on C.
Okay. Yeah. So, but
There's other ways it goes.
but inside a two-port system,
It could be loss.
Yeah.
Right. And it depends on a whole bunch of things. But if it was like, for example, a resistor, S21 would be less than 1.
Yeah.
Right. If it's an amplifier, could be actually. If it's an amplifier, it could be that. Doesn't mean anything, right? Because I mean, it could be a very amplifier, so it's close to that.
Okay.
Right. So it really depends.
Yeah.
Right. So.
Yeah. Cool.
All right. Excellent.
Yeah, thank you.
Okay. Cool.
So do you have any idea yet of when the mid-sessional exam is going
Yes.
to? Oh, cool. Okay, perfect.
So just 24th, September 24th, Tuesday at Wilson Hall.
Okay.
So it's this time on the 24th, Wilson Hall.
Do you know if it's before or after the summer break, the spring break?
Before.
Before? Yeah, cool. Perfect. Okay, good. Thank you
All
very
right.
much.
I've done it the week before, and I've done it before on the Tuesday, so therefore it gives you some time to study, over the weekend and all that kind of stuff.
Yeah, that's cool. That's a very good option. Like, I mean, I have one of my modules is lasting from the week of the summer break.
Okay.
So it's just a lot better for me if it's before.
Yeah, it is. It's definitely before.
Cool. Thank you. Have a
No
good
worries.
day.
Yeah, same.